To Gokul Global University e-learning. Our today's topic is cycloconverters, which falls within the subject power electronics 2. In our previous lectures, we have discussed about the AC voltage controller. So, can anyone tell me what is AC voltage controller? So, you might have recalled that AC voltage controller will do a conversion from AC to AC without change in frequency, but a certain industrial applications which requires a conversion from AC to AC as well as with a variable frequency. So, in a prior days, that task was achieved by using transformers, tape changers, etc. But with the advancement in power electronics devices, there is a new technique. With the use of power electronics device, we can directly convert the AC to AC voltage with the variable frequency, and the device, the arrangement of switches are such that the device is called as AC CYCLO-CONVERTER. The CYCLO-CONVERTER is within the family of AC to AC voltage controller, but it can both vary the frequency and voltage. The CYCLO-CONVERTER directly converts AC signal of one frequency to AC signal of variable frequency. It means the frequency is usually a line frequency and which can be varied with the use of AC CYCLO-CONVERTER. And these variable frequency AC signals can then be used to directly control the speed of AC motor. Thyristor based cycloconverters are typically used in low speed, high power application of certain megawatt for driving induction and wound field synchronous motors. So, what is the basic principle of cycloconverter? The basic principle of cycloconversion is illustrated by single phase to single phase conversion shown in basic diagram of cycloconverter. Within the box where it is written cycloconverter, it contains several circuits, and while the circuit is supplied with the fixed AC power, there will be internal manipulation within the cycloconverter, and at a load terminal you will observe a variable AC power with a different output frequency than at this frequency. This is a single phase to single phase cycloconverter basic diagram. You can observe here. You might have recalled in power electronics 1 you may have studied about the duality principle, and in that case you may have observed this type of diagram. This is a single phase to single phase cycloconverter in which we have employed 4 thyristor in a positive converter and the 4 thyristor in a negative converter. Within the positive and negative converter we have employed here the load. Which type of load is this? This is nothing but a AC load. In duality principle you might have observed this current which is shown by ID, that is nothing but a circulating current, then voltage supply, that is AC, and the output voltage will also be AC voltages. The P type converter or positive converter called, and this is N type or negative converter. There is a two nodes A and B will be a supply voltage. Here also the same, you can observe here A and B. You might have observed that the direction of all this thyristor or a positive converter will be in a upward direction, and the direction of this is in the downward direction. So this is nothing but the circuit arrangement of single phase to single phase AC cycloconverter. Now you can draw this diagram in your notebook separately, thus we can later on see the different waveform or explain the different waveforms. Here in our diagram we have applied voltage source, and as we have discussed, the voltage will be AC. So here it is given by AC voltage. Then again the output voltage. So output voltage, if you consider the firing angle of this gate pulse is as a 0, then your thyristor will behave like a diode, and as you know, the diode is an uncontrolled switch. So your waveform will be start to conduct from this or initial 0. Okay, again when positive cycle will conduct, you can only achieve positive waveform, and when the negative cycle or the N type of converter will in use, then you can have the negative cycles. Mind it, you cannot turn both the cycle in a single time. You cannot control in a single time. The conduction of this thyristor or the P type of N type of converter are simultaneous. It means one after the another. So you can observe this type of waveform if your alpha angle is 0 for positive as well as negative thyristor pair. Now let us assume you have applied alpha to a certain angle at 60 degree, then you will observe the waveform like this. The energy, as we have discussed in AC voltage controller, that the given energy is full cycles, while the energy of alpha angle will reduce due to the cut down of the initial 0 to alpha will be cut down. So the output waveform will be somehow less than that of a input waveform. As well, the frequency you can observe here. There are 1, 2, 3 and 4 full cycle. You can see here there are 4 full cycles in voltage supply, 2, 3 and 4 waveform. But at output voltage you can observe that is only a single AC voltage you will observe. It means the 1/4 of your initial frequency you will achieve. So frequency will be reduced and voltage output is also reduced. So the purpose of our cycloconverter, that is to convert the or to achieve the variable frequency, is fulfilled here. Now it is the alpha varying for different pulses or within the range of 0 to pi. There are, you can observe the waveform. Now, to understand the operating principle of cycloconverter, this is nothing but what we have discussed, but I just read it. To understand the operation principle of cycloconverter, the single phase to single phase cycloconverter should be studied first. This converter consists of back to back connection of two full wave rectifier circuits, that is positive converter and negative converter. Figure shows the operating waveform for this converter with resistive load. Okay, this is one more important point that we have discussed it with the resistive load. You can employ here the RL and RLC circuits or at that type of load. The input voltage Vs is in AC voltage at a frequency as shown in figure. For a easy understanding, assume that all the thyristors are fired at alpha is equal to 0 degree. That is, thyristor acts like a diode, as we have discussed. Note that the firing angles are named as alpha p for the positive converter and alpha n for the negative converter. Consider the operation of the cycloconverter to get 1/4 of the input frequency at the output. For the first two cycles of Vs, the positive converter operates supplying current to the load. It rectifies the input voltage, therefore the load sees 4 positive half cycles as shown in the figure. The next two cycles, the negative converter operates supplying current to the load in the reverse direction. The current waveform are shown in the figure because the resistive load current will have the same waveform as the voltage but only scaled by the resistance. Note that when one of the converter operates, the other one is disabled, as we have discussed, so that there is no current circulating between the two rectifiers. Thus, by varying alpha, the fundamental output voltage can be controlled. One, from the waveform you can recall the waveform that one is input voltage, two is the output voltage with 0 firing angle, third one was the output voltage with firing angle alpha pi by 3 radian or 60 degree, output voltage the waveform fourth, output voltage with the varying firing angle. Constant alpha operation gives a crude output voltage waveform with a rich harmonic content. Thus, dotted line in the figure 3b and c shows square wave. If the square wave can be modified to look more like a sine wave, the harmonics would be reduced. For this reason, alpha is modulated as shown in figure 3d. So, while we are modulated the alpha for different angle, then we can more accurate sine wave at output terminal. Now the 6-stepped dotted line is more like a sine wave with fewer harmonics. The more pulses there are with different alphas, the less the harmonics. Now up till now we have discussed single phase. Now this is a 3-phase to single phase cycloconverter. Okay, 3-phase to single phase cycloconverter. You can observe here the pair of positive converter and pair of negative converter. The circulating current will also given and the load is also shown here. There are 6 positive thyristor in the upward direction and the 6 negative thyristor or reverse bias thyristor or downward direction you can observe. Okay, this is looks like a prior diagram. There are 6 thyristor is shown with the positive converter and 6 thyristor with the negative converter. We have discussed. You can observe the waveform for positive and negative converter as a 1 and 3, and when we are applying cosine timing waves, we can achieve a reference wave like this. The 3-phase to single phase half wave cycloconverter. There are two kinds of 3-phase to single phase half wave 3-phase cycloconverters. 3-phase to single phase half wave cycloconverter and the 3-phase to single phase bridge type cycloconverter. Like the single phase case, the single phase to 3-phase cycloconverter applies rectified voltage to the load. Both positive and negative converters can generate voltages at either polarity, but the positive converters can only supply positive currents and the negative converters can only supply negative currents. Thus, the cycloconverters can operate in four quadrants. You can see here four quadrants. In one, both are positive. Voltage, suppose let us say that is a current, this is my voltage, then both are positive. Quadrant 1. Second, both are negative, that this current is negative and voltage is negative. Then this mode are called the rectification mode. 1 and 3rd will be the rectification mode. While the current is positive, voltage is positive and current is negative, this mode, and voltage is negative and current is positive, this mode. So this will be your inversion mode. The modulation of the output voltage and the fundamental output voltage are shown in figure as we have discussed. Note that alpha is sinusoidally modulated over the cycle to generate a harmonically optimum output voltage. Converter output voltage to cosine timing waves, and the third, negative converter output voltage. The polarity of the current determines if the positive or negative converter should be supply power to the load. When the rectification mode, it will give a supply to the load, and in the inversion mode, it will take the supply from the load. Conventionally, the firing angle for the positive converter is named as alpha p, and that for the negative converter is named as alpha n. When the polarity of the current changes, the converter previously supplying the current is disabled and the other one is enabled. The load always requires the fundamental voltage to be continuous. Therefore, during the current polarity reversal, the average voltage supplied by both of the converters should be equal. Otherwise, switching from one converter to the other converter, one would cause an undesirable voltage jump. To prevent this problem, the converters are forced to produce the same average voltage at all time. Now 3-phase to 3-phase cycloconverter, you can see in the diagram there are 6 step thyristor pair are connected, or 6 step rectifier pair is connected. You can see in the anti-parallel direction. 3-phase to 3-phase cycloconverter, this is also same. This is 3-phase to 6-phase cycloconverter. This is bridge type cycloconverter. If the output of 3-phase to single phase cycloconverters of the same kind are connected in delta, and if the output voltage are 2 pi by 3 radians phase shifted from each other, the resulting converter is a 3-phase to 3-phase cycloconverter. The resulting cycloconverters are shown in figure 7 and 8 with the connection. If the 3 converters connected are half wave converters, then the new converter is called a 3-phase to 3-phase half wave converter. If instead bridge converter are used, then the result is 3-phase to 3-phase bridge cycloconverter. 3-phase to 3-phase half wave cycloconverter is also called a 3-pulse cycloconverter or an 18 thyristor cycloconverter. On the other hand, the 3-phase to 3-phase bridge cycloconverter is also called a 6-pulse cycloconverter or a 36 thyristor cycloconverter. The operation of each phase is explained in the previous section. The 3-phase cycloconverters are mainly used in AC machines, drive systems running 3-phase synchronous and induction motors machines. When cycloconverters are used to run an AC machine, the leakage inductance of the machine filters most of the higher frequency harmonics and reduce the magnitude of the lower order harmonics. Now in this slide you can see output voltage equation for the cycloconverter. What is the output equation? The output voltage waveform for a M phase converter with a firing angle alpha is shown in figure with the time origin pp dash. Here P to P dash taken the peak value of the supply voltage. The instantaneous phase voltage is given by E is equal to Em cos omega t, or it is given by root 2 E phase cos omega t, where E phase is supply voltage per phase. This is my P, this is pi by M, and this is minus pi by M. The total period of a peak output voltage you will observe, that is 2 pi by M. This is due to the overlapping of your thyristor. This is overlapping. From figure it can be observed that the conduction period is from minus pi by M to pi by M. If the firing delay is alpha is equal to 0 for the firing delay angle alpha, the conduction period is from minus pi by M plus alpha to pi by M plus alpha. From the above cases, the total conduction period is 2 into pi by M. The average value of the output voltage is given by EDC, that is M by 2 pi integration from minus pi by M plus alpha to pi by M plus alpha root 2 E phase cos omega t dt d omega t. It will give us final solution as root 2 E per phase pi by M by pi into sin pi by M cos alpha. This expression is obtained for DC to AC conversion in module 2 and also available in textbooks too. When the firing angle is alpha is equal to 0 degree, EDC has maximum value of EDO is equal to root 2 E per phase M by pi into sin pi by M. If the delay angle in the cycloconverter is slowly varied as given earlier, the output phase voltage at any point of the low frequency cycle may be calculated as the average voltage for the appropriate delay angle. This ignores the rapid fluctuation superimposed on the average low frequency waveform. Assuming continuous conduction, the average voltage is EDC is equal to ED0 cos alpha. If E0R is fundamental component of the output voltage per phase for the cycloconverter, then the peak output voltage for the firing angle 0 is root 2 EOR is equal to EDO is equal to root 2 per phase E per phase pi by M by pi into sin pi by M, or EOR is equal to E per phase M by pi dot sin pi by M. Now what is DC link converter? So in period days what we are doing? We are doing to convert a 3-phase AC supply with the help of cycloconverter or rectifier. We can convert it. Then we are employed DC link or the capacitor between them here, and then again whatever the AC we have given, whatever DC we have received, again we are converting it with the help of inverter. We are converting to a AC, and then it will supply to the load, and this is called a DC link converter. What DC link converter? It will also do the same work as a cycloconverter. It will convert the AC to a variable DC. The cycloconverter is normally compared with the DC link converter, where two power converters or controllers. First one for the converting from AC input at a line frequency to DC output, and the second one as the inverter to obtain AC output at any frequency from the above DC fed to it. The thyristors or switching devices of transistor family, which are termed as self-commutated ones. Usually the former, which in the case is naturally commutated and used in control converters or rectifiers. The diodes, whose cost is low, are used in uncontrolled ones. But nowadays, switching device of a transistor family are used in inverters. Through thyristor using force commutation are also used. A diode connected back to back with the switching devices, maybe power transistor, is needed for each devices. The number of switching devices in a DC link converter depends upon the number of phases used at both the input and output. The number of devices such as thyristor used in cycloconverters depends on the type of connection and also the number of phases at both input and output. It may be noted that all features of a cycloconverter may not be available in DC link converter. Similarly, certain features like PWM techniques as used in inverter and also in converters to reduce the harmonics in voltage waveforms are not applied in cycloconverters. What are the advantages of cycloconverter? The first and main advantage is that we can achieve a variable frequency. The output frequency can be varied from 0 to rated value, with the upper frequency limit being decided by the turn of time of the switching devices, which is quite low due to the use of transistor in the recent time. The control circuit here is simpler as compared to the used in cycloconverters. It has high input power factor if diode rectifier is used in the first stage. If phase control thyristor converter is used, power factor depends upon the phase angle delay. It is suitable for higher frequencies too. What are the disadvantages of cycloconverter? The conversion is in two stages using two power controllers. One is as a converter and other as the inverter. Force commutation is required for the inverter if thyristors are used, even though phase control is used in converter where natural commutation takes place. The feature of regeneration is somewhat difficult and also is involved to incorporate in a DC link converter. The output waveform of the inverter is normally a stepped one, which may cause non-uniform rotation of an AC motor at a very low frequency, less than 10 Hz. The distorted waveform also causes system instability at low frequency. This can reduce by the using PWM techniques. Where are the which is the application of cycloconverter that is being employed in cement mill drives, shape propulsion drives, rolling mill drives, series drives, or grinding mills, mine winders, etc. Thank you. If you find any questions or any doubt, you can comment it in our YouTube videos. Thank you.